that 8-foot copper rod that's hammered into the ground that your copper wiring attaches to. It says let's just we're gonna get into a little bit more detail. The grounding electrode can actually be a couple of different things. It can be a metal water pipe. If you're building a concrete foundation and you're building rebar into that foundation, it is possible to use the rebar as the ground, but it's very difficult to. What you have to do is have 20 feet of continuous rebar, not 20 feet of total rebar, but a 20-foot long stick, or otherwise not just tie wrapped but welded together rebar, for it to be considered to be good enough as a ground rod. And that's because concrete is less conductive than soil. And so, they say, well, if you're not putting a ground rod in soil, then we're going to subject you to a little bit more of a, harsh oversight. This grounding electrode is now in concrete, so you need more metal in that concrete to have equivalent conductivity. Similarly, it's common in grounding to use a number 6 bare copper wire. Sometimes it can be even smaller than that, but number 6 is very common for 200 amp electrical service. They say if you're going to use, if you don't have 20 feet of rebar, there are certain circumstances where you can use bare number 6 as your grounding electrode instead of a ground rod. But if you're in concrete, they're saying you got to use number 4 as the minimum size if you're using copper wiring. So when can you use bare, copper wire as the ground? Well, you could circle the whole building with number 2 wiring. Usually that results in a higher cost, but not all soil is good for ground rods. Some soil is not very conductive. Dry soil is not very conductive. Rocky soil is not very conductive, and nor can you dig down very deep. And so it might be that to actually get good grounding, that you have to implement a much larger ground ring in very extreme soil types. If you're building your on top of a rock shelf, you might not be able to chip much rock out of there. But for most soils, we're using a ground rod. That ground rod should not be less than 8 feet in length. It can be, you're running the copper wire up to the ground rod. I get really concerned about this connection over the long run. On a recent project, we were using CAD welding, which is a little old school, but we were actually welding this connection rather than relying on the bolt. And I thought that was, once we got the hang of doing CAD welding, I thought that was a better way of doing it. Although finding the actual CAD weld is the difficult part. Okay, so there are ground rod resistance tests. And if you aren't testing 25 ohms or less, then you put in a supplemental ground rod. I think putting a supplemental ground rod in anyway is not a terrible idea. It's good to have some redundancy. You can't have a redundant neutral to ground connection, but you can have a redundant ground rod. The thing is, if you're putting in 2 ground rods to improve resistivity, you should note that electricity to ground is being dissipated over a surface area, and the ground rods, if they're right next to each other, won't increase your resistivity unless they're spaced apart. So required additional grounding electrodes need to be spaced apart. But you're also allowed to put in auxiliary grounding electrodes that are just purely redundant, so that if one connection to one ground rod fails, you're still connected, and those are subject to the same rules. You'll have one ground rod per building. So it says, when not exposed to physical damage, number 6 or larger is permitted to be run along the surface without building protection as a grounding electrode. So where this comes into play is up on a rooftop. You got your solar array, and you have your solar rails kind of running across the rooftop. The question is, how do you ground the metal solar rails and the metal module frames? And the answer is, well, you run a ground up there. And so here's our grounding electrode, on the side of the building. There's different ways you can run your DC ground through the home. What I commonly do is I combine the DC ground with the AC equipment ground conductor and run the DC ground through the equipment ground conductor down to the ground rod itself. So I'm running my ground back to the inverter, and then I'm taking the inverter ground and the AC out, running it with my AC output circuits, and getting back to the house that way. The main thing when you're piggybacking off the AC equipment ground is that there's sizing requirements for the DC side ground, and there's size requirements for the AC size ground, and you just need to check to make sure you're using the larger of the two. And so if the smallest DC grounding electrode size is number 8, then you need to make sure, if you're using the AC equipment ground conductor as your DC pathway to ground as well, then it needs to be sized to accommodate that number 8. Sometimes these AC equipment grounds can be a little bit smaller than that. An alternate common solution, and so I'll usually run my ground as number 8 up to the rooftop internally. Another common solution, though, is just to go one size up into number 6 and just run your number 6 cable from the ground rod, straight up the building and onto the roof directly. And you can just run it in bare number 6 by itself without protection, without conduit. You can run bare number 6 alongside the building, provided that it's not exposed to physical protection, such as running along the side of a driveway. There's a difference between the side of the building or a place where there's higher likelihood for physical damage. And this DC electrode should be continuous. So, what that means is that run from the array rack on the DC side to where it might land onto the AC equipment ground conductor needs to be a single piece. Or the run from the ground rod up to the rooftop needs to be a single piece. If you do cut it, then there's certain rules about crimping it back together to essentially ensure that you don't ever disconnect the ground of the system. What would happen if you disconnected the effective ground path of a system? Well, if your solar panels started faulting into the metal module frames, and those metal module frames were not grounded to anything, they would just have high voltage, and it's likely that nothing would happen. Well, that sounds pretty good, right? Nothing happens, so no fires are breaking out, no electrons are flowing. Well, yeah, but it's a death trap. I mean, if someone is walking along the roof and they have enough resistance to ground and they touch that high voltage module frame, they could electrocute themselves. So, we want faulting electricity to be able to have a path to ground, even if that might mean bad things are happening. They shouldn't be happening to begin with, and we're trying to manage that failure point. Okay, so if you're running to a ground rod or a ground pipe or a ground plate, your ground does not need to be any larger than number 6. So another reason why number 6 bare is commonly used as a ground is it is like a one size fits all solution. If you're using, it's common to use a ground rod or a ground plate, and so you do your calculations, and it says your ground needs to be so large. If you have a ground rod or ground plate, code says it doesn't need to be larger than number 6. This can commonly get overruled by local jurisdictions to say under that's fine, but in our grid, it's a 200 amp service, and we're going to require you to have a number 4 ground. They might not allow you. A local jurisdiction rule would say you're not allowed to use that exception. And I've come up across it, and I've asked the inspector about it, and his response was, well, in this region, our soil doesn't get very good resistivity, and so we want to make sure that it's everything is sized to the max. Okay, that ground rod doesn't that the grounding electrode conductor, the thing that connects the service panel to the actual ground rod itself, that doesn't go down in the soil. But anyway, so there are rules that govern the minimum size of your grounding electrode conductor, they're basically based off the size of the feeders going into the home. That says, hey, this 2-aught to 3-aught cable, that's capable of holding this much amperage. And so, we're not requiring the ground path to be of equivalently sized amperage, but there is a minimum that we do require. And so solar, we're normally dealing in like number 10 cable or number 8 cable. And this is saying if your service entrance conductors are number 2 or smaller, you can use a number 8 ground. And this is, commonly for residential size solar projects, the smallest ground that you need is number 8. Not too hard to upsize it to number 6 and avoid the need for running it through bare copper, or through conduit. You can use bare copper instead. And then, but just keep in mind, when you start getting into 200 amp services or larger, the size of that grounding electrode conductor does in fact increase. Unless you're using one of the exceptions, and of course that would require the local jurisdiction not to have any special rules. Okay, this is a good one. What we're seeing is conduit coming into a box. And so when I got started learning about electrical, I was like, okay, well, we got metal conduit, and the metal conduit goes into a metal box, and that means the metal conduit can be used as a ground path. And I'm looking at the metal water pipe being used as the grounding electrode, and I'm thinking, man, we're using the metal conduit as a ground path all the time. That's not really true. Often you'll run a equipment ground conductor inside that metal conduit so that you don't have to worry about it being the ground path. And the reason is there's certain conduits, there's certain metal conduits that are not registered to be an effective ground path. Like if it's not a clear continuous stick of tube, but is instead kind of a spirally flexible coily cable, it might not be rated for a ground path. The box itself matters as to whether or not this is grounded or not. So you got your metal conduit, and it's coming into this box, and we got these holes in these boxes. But see in the background here, we have a hole that has different sizes. There's an inner hole, and then another hole, and then another hole, and that's so that it's easy to have a hole of different sizes in the box. Go figure. Well, this is also an impaired connection in the box. That little dimpling of the metal reduces its resistivity. And what that means is if I want to have metal going into a metal box with a regular lock nut and nothing special going on, that only constitutes a grounded path if I'm using the outer ring of that box. If I'm using the inner ring, then I still have that dimple. It's still an impaired connection. If I'm using the outer ring, it's continuous and smooth. And what happens is if you're going into, say, a plastic box, or if you're going into an impaired connection, you can buy these little lock nut attachment points that come with a little terminal to run some copper wire to, so that you ground the conduit. That metal conduit needs to be grounded one way or another. So you're either grounding it to the box or you're grounding it, to a piece of copper that comes and then lands on a ground bar inside the box, and other grounds can be coming off of that as well. So impaired connections cannot be ground paths. You have to make sure that these couplings and fittings are made up tight. If they're loose, if they're not tight, they're not going to be an effective ground path. It says MC cable is acceptable. We're looking at some grounded conductors. We got there's various different kinds. Well, we're going to save that for a wiring and conductor discussion. One important thing to know is you'll be on site and seeing equipment grounds that are in a green jacket. And again, it's number 4 or larger can be taped green. Anything smaller than that, other than bare copper, has to be in a green jacket if it's the equipment ground conductor or the ground wires. So a lot of these projects, the difference between a do-it-yourselfer and a professional contractor is going to be, for cables that are number 6 and smaller, are they using colored cables or not? Are they organized enough to not just buy one big spool of black cable and that's it, or are they buying the actual spools needed for the job as they go? That can also be an indicator of how much business they do, for that matter. If you are increasing your cabling sizing, then you'll need to increase the size of your equipment ground conductor, unless you're using a ground rod with bare number 6. It's sized for the highest amperage device along the raceway. So now we're looking at not the grounding electrode conductor, but the equipment ground conductor. So remember, the grounding electrode is the final stop on the station. Then you get to your service panel, and all the other grounds that come off the service panel, usually there's a little bar that they're all wired into. Those circuit level grounds are the equipment ground conductors, grounding all the equipment back to the service panel. And so these are based off the breaker size rating. It'll size the equipment ground conductor. And so I guess what I'd say is a lot of solar is on 40 or 50 or 60 amp circuits, and its minimum equipment ground conductor size is number 10. You might get an inspector that says, I also want to see a DC side grounding electrode run up to that rooftop. and then the minimum size when using a ground rod is number 8. So often this leads to a material discussion we have in other classes over good material selection. I'll do an MC metal clad cable, and I'll upsize that to number 6 because it comes with a number 8 ground. And then I have all of my grounding requirements as well as solar cable all bundled in one flexible cable that I can easily run through an attic space. So we're going to talk about that. Might be first thing tomorrow. So we have direct current systems that are less than 300 volts should be grounded. But greater than 6, we're going to talk about that when we get to the solar and battery sections tomorrow. The size of the DC grounding electrode, it's kind of the same rules as the AC electrode. Not smaller than number 8. Ungrounded DC separately derived systems shall have a grounding electrode conductor connected to the electrode. Not all solar systems are separately derived, but all this is really saying is that if you have standalone systems, they all still need to be connected to the building ground one way or another. And it's all metal parts, all enclosures, all boxes, all raceways, all exposed non-current carrying metal parts need to be connected up to the grounding system. Okay, so we made it through the first half of electric code, which is section 200. We're getting into wiring methodology. Let's spend a few minutes on this, make some headway, make sure we have enough time for solar and batteries tomorrow. We have so these are wiring methods, and here's one for going through wood members. So contractors will run power through the studs and through the beams, and it says, okay, you have to be 1.25 inches away from the nearest edge of the wood member. Otherwise, you need to put a steel plate on that wood member, basically to prevent people from drilling into the wiring. If you're drilling in, mounting something on the wall, you could be drilling into a stud, and you have to be stepped back from that by 1.25 inches. Similarly, when you're running underneath the roof, you need to be over 1 inch from the underside of that roof surface. And so if you're in the attic and you're running your conduit along the rooftop, you can't just put it right up next to that roof deck. You need to give yourself a little bit of room, to imagine that someone down the line is hammering a nail through, giving yourself some damage, some room. Here's another one, warning ribbons, so that when you're doing underground work, putting cables and conduits and anything underground, when you're filling in that trench, you need to put a warning ribbon so that people, if they're digging in that area, the first thing they encounter is the ribbon and not the electrical devices. It's kind of interesting. You can splice and tap a cable without going into a box for underground. Backfill, you don't want any rocks or sharp objects. This is the kind of a debate in electrical industry. Do you do conduit or direct burial cabling? Direct burial cabling is so much easier than going into conduit that power companies do direct burial all the time. But it really depends on what your backfill is going to be and then what's on top of it pressing it down. So when you're going over roadways or motorized areas where you have heavy machines on top of the surface, then you might have a need for more physical protection. And then you have to account for earth movement in areas where you have freeze thaw conditions and you're going from frozen ground up to non-frozen ground, having expansion fittings and S loops, uh, expansion fittings for thermal expansion on the rooftop for that matter. All right, so now we have raceways exposed to different temperature differentials need to be sealed. We have a requirement for electrical continuity of raceways. So we already saw, entrances needing to be sealed in section 200. It's repeating it again in section 300. This is a useful one. Short sections of raceways used to provide structural support or protection do not need to be part of the electrical continuity section. So if I have a footing, if I have a pipe boot and it has a piece of unistrut on it and it's supporting some conduit that's running across the top of the rooftop, how far does this grounding stuff go? Do I need to ground the all thread and the unistrut and the pipe boot? It says support sections. And even you could argue that if you have a box here and a box here, a little 6-inch tube that connects the two together would similarly be a short section for physical protection. Are generally not subject to the same temperature derating and conduit sizing considerations that larger, anything more than a foot, I'd say. Here it's kind of saying, well, so that's kind of interesting. You don't have to overkill your concern about electrical metal continuity. With AC side stuff, you have to be a little bit concerned about the space between individual conductors going into metal because of induction. DC is not, that's not a concern. There's also requirements in this section for conductor bend radiuses, and I think that can kind of mess up a designer where you have to account for the actual size that it takes to bend the wire around a turn. And that might mean, if you have a large box with a sharp 90-degree turn, you have to use the large box and not the small box. It can also mean when planning your space requirements where your conductors and stuff come down, you have to start planning, your space for the bends. This is just common workmanship that electricians do, standard practice. Again, we see the parallel requirement for 1/0 cable for the conductors in parallel. And the main thing when you are dividing into parallel runs is that the raceways, the individual divided out sections, have the same characteristics. You don't put all of your leg ones in one conduit and all of your leg twos and grounds and neutrals in another. You divide up the amperage evenly, you divide up your neutral evenly, you divide up your ground evenly. Capacities for conductors that are under 2,000 volts. And it says, look, we have to consider a few things. What's the temperature outside? What's the temperature because of the circuitry? The same temperature that opens up the breakers is inside those conductors, and those conductors will, they're wrapped in some plastic, but they will radiate heat. And then what's the heat dissipation rate? If I put all these conductors inside a conduit that's enclosed for physical protection, now I've eliminated the airflow around the conductor and put a whole bunch of conductors in there. So, if there's a conduit that is full versus a conduit that has more empty space, and then just the nature that it's in conduit, all those things are going to increase the temperature on that conductor. And so all of these things will impact the ampacity of the conductor. And then after you get that, you might apply, an additional 25% protection to whatever this spits out. Or you could, as an electrical engineer, you may be allowed to perform the actual calculation and stamp it to say, actually the temperature derating is not going to be that bad. I know precisely what it's going to be. The temperature correction factors in code are to get around doing engineering calculations, so that electricians don't need to know the math, but can still install electrical devices in a safe manner. Okay, so we have some adjustment factors. The first is if there's more than 3 current carrying conductors in a conduit. And then I say, look, short sections, this does not apply to. We're not concerned if there's a box and another box, you're just doing a short run and running all your cables from one box to the next. We're not concerned about the temperature adjustment in that situation. We're concerned about the conduit, that's going, 100 feet, 200 feet in the other direction, on what the temperature differential is going to do to this center cut, the least amount of airflow. So this ampacity derate does not apply to those short sections, near the inverter wall, but rather the long sections between the inverter and the array, or between the inverter and the point of interconnection. This is kind of interesting. It can apply to underground cabling if they're not spaced appropriately apart. And so in commercial design work, you're going to get spacers for your conduit conductors that go down into a trench to space them out enough for better heat dissipation. One of the other items that's been bouncing around in code a whole bunch, and it continues to be changed, is the temperature for thinking about ambient temperature. A rooftop is the hottest part of the building. It's hotter on the roof than it is in the attic as far as maximum temperatures go. And so we have outside of conduit cable in solar on the rooftop, and it can be exposed to direct sunlight. But on top of that, you would also have conduit on the roof being exposed to direct sunlight. And it says, so if we have raceways or cables exposed to sunlight, direct sunlight on the rooftop, you need to have a 1 inch, or technically greater than 7/8 inch. You need to have a 1 inch clearance up off of that rooftop. If not, in most circumstances, you can maintain that 1 inch, but there are certain, special circumstances where you may not. Let's say that your cable is already oversized to accommodate the ampacity after the temperature derating. So you're already oversizing your cable, maybe not for amperage, but for voltage. And so if you're already oversizing your cable because of voltage, you might have the amperage that you need to adjust for the temperature differential, and then you'll say, okay, well, I'm just going to stick to the rooftop. But there's devices you can get now in the solar industry to support cable and conduit up off of the rooftop, even while you're making those runs. If you don't maintain that 1 inch clearance for whatever reason, you have to add 60 degrees to the temperature differential. And so we're going to take a closer look at that, but that is quite a steep temperature adder. This section of code used to be 0 to 1 inches, and then 1 to 3 inches, or 1 to 4 inches, and then above 4 inches. And they had different derate factors for the like. Since then, they've gathered more data and said, you know what? There's really not much difference between 4 inches above the roof and 1 inch above the roof. And so we're going to simplify things. And now, instead of being a table, it's just an inch above the roof. You're good for not adding temperature, as long as you just designed it ambient, and that's fine. But if you're right on top of the roof, you're collecting more heat from that rooftop, and we need to increase the temperatures accordingly. The neutral wire in this case does not count as the current carrying conductor, because that neutral is only going to be carrying the imbalanced load between the two loads, and your load A and load B. That neutral, when it has current in it, is going to have less current than if the two power cable conductors were at full blast, evenly balanced. So it doesn't count as a current carrying conductor. Neither is the system ground, for that matter. And so you count up your current carrying conductors, and it can result in a discount. If you have 20 or more conductors crammed into a single conduit, you could be discounting your ampacity by over 50%. So where we will kind of end with is that there are tables in National Electric Code that can be a little intimidating at first glance to read, that say, okay, well, we have our conductor temperature rating, and different cables have different temperature ratings. Solar cable tends to be on the high end of the temperature rating. Sometimes indoor AC Romex, might have a bare minimum temperature rating, because it's not designed to be used in high temperature environments. Underground cables that are just standard may have a higher temperature than an indoor cable. So that comes into cable jackets, and that's included in the code. We're just not there quite yet. So we have the temperature condition of the jacket, and then we have the actual temperature that it is outside. Our operating environment. Are we in a freezer, or are we on a rooftop? And you say, okay, well, the conductor is sized for, let's just go down. This is 90 C temperatures. And the last thing is this final key here that says it's based on a 30 C or 86 degree Fahrenheit design condition. And this is really confusing, but the ampacity tables from code, when they give you the ampacity capability of the conductor, they're giving it to you at a particular temperature. So you'll have a table of all the conductor ampacities, and it'll be like, this is all the ampacities at 86 degrees Fahrenheit. Well, I'm not at 86 degrees Fahrenheit. I'm up at the rooftop at 160 degrees Fahrenheit. And so this temperature correction factor table says this is where you adjust the ampacity based off ambient temperature. It says if your normal ampacity is X at 86 degrees Fahrenheit, then if you're installing at 160 degrees Fahrenheit, then you need to discount that ampacity by almost 70%, because you're at such a higher temperature. Or you could use higher temperature rated cable, and then you'll only need to discount it by not so much, by 40%, instead of by 70%. And they're saying, okay, when with the 60C conductor, we're not even going to allow you to consider using it in this high temperature environment. And so these temperature, to kind of conclude our program today, these temperature correction factor tables are first step. You get the ampacity from a different table, and you look up at the table title and you say, okay, well, this is the ampacity at 86 degrees Fahrenheit. And then you go plug it into the 86 degree Fahrenheit temperature correction factor table to get your temperature correction factor based on the temperature rating of the cable that you're using. So, it's a connecting point A to point B to point C to get your temperature correction factor, but it's really not any more complicated than that. So lastly, in context of the cables being within 1 inch of the rooftop, where does that 60 degree Fahrenheit temperature addition get you? And it's saying, okay, well, if I'm at a maximum rooftop temperature of 130 degrees, and then I add 60 degrees to that, that would be, normally I'd be discounting the ampacity of those conductors by 25%. Because of the added temperature, but now I'm discounting them by a whopping 70% because of temperature. And it might also be the difference between being able to use 75C cable on the rooftop and, if we add 60 degrees, we're off the chart. We don't have an option down here, that could be indicating that 75C rated cable 1 inch from a roof surface would be beyond its spec, and that could cause a fire. So it's that having your cables be 1 inch to the roof adds a tremendous temperature adder to that should be avoided if possible, and only utilized if you are very well familiar with your design and you know that your cables are so large that even if you're discounting them by 70%, you still have the ampacity clearance that you need. Okay, so with that, we are out of time today. Tomorrow we will get out of section 300 and we'll go and cover, the battery sections and the solar sections in a similar, scrupulous, every important detail need to know. So thanks for sitting through this class. I know it's a little bit of a dry content, but it will help you get much more familiar with National Electric Code. And so the goal is, now you'll be able to get a copy of Codebook, thumb through it, be a little bit more familiar with what's inside.